attention mechanism is just a way to route information between parts of the sequence. And that's the genius behind a transformer. Layer by layer, it routes information to the correct place in the sequence, such that it understands the entire thing at once.
Getting a paper accepted into a top-tier conference like ICML or NeurIPS, and getting the interest from the research community comes with the pressure to surpass the previous state-of-the-art.
Do you remember when GPT-2 was released, or indeed wasn't released because it was too dangerous? It had about 1.5 billion parameters in it. It was a Transformers language model. It was trained on a corpus of about 40 gigabytes of text, but it was highly curated. Fast forward 1 year, and Microsoft have just released a new version, pretty much of the same model, that has 17 billion parameters. 18 billion. Doesn't matter. It's a lot. In the olden days, we had these static, brittle knowledge graphs. They were handcrafted. It was incredibly onerous to create these things, but if we wanted to do something like question and answering, it was the only way we could do it. If we wanted to say, what year did we win the Second World War? Without some kind of an ontology of information, we couldn't capture it. These transformer, transductive language models that we have, you can pre-train them on a large corpus of text, let's say Wikipedia, using this self-supervision task, and then you can fine-tune it on a downstream task. And the incredible thing is that these things just accrue information. They accrue knowledge about the world. You can ask it, how old is Obama? And it will know the answer. It's incredible. The current revolution in neural representations for natural language originated with Mikolov's word-to-vec, the skipgram model in 2013. And it was such a simple architecture. It used a contrastive loss, which we spoke about last week, and it just asked the simple question, does this word belong in the context of this other word? Just using a fully connected architecture and a negative sampling strategy with a contrastive loss, you could project these words into an embedding space that reflected their linguistic context. Okay, fine. But the problem is the words were atomic. The words didn't really take into account the structure, and language has this incredible structure. Words can modify each other from a long distance, and those relationships can be multi-scale and complex. So the first evolution along the road was we started to have language models like Elmo, which started to use bidirectional LSTMs to model the dependencies, the adjacent sequential dependencies between tokens. And this was starting to capture some of the meaning encoded in language. Now, ULM-Fit came along, and this is when things really started to get interesting, because ULM-Fit by Jeremy Howard and Sebastian Ruder, this was the first model that essentially did transfer learning. So you could build a language model that was just predicting the next word using a bidirectional LSTM. But then, exactly the same as what happens in computer vision, you can do transfer learning. You can just take off the last few layers, and then you can put a classifier on, and you can get it to do something completely different. So pre-train a language model on Wikipedia, take the last layer off, turn it into a classifier, and do sentiment analysis. You've got that transfer of knowledge between the self-supervised pre-training task, and that essentially means we've got more training data, and the language model already knows loads and loads of concepts which will be useful for our downstream task. Now, 2017 was an interesting year. This is when a chap called Vaswani came about from Google. He brought in a paper called Attention is All You Need, and this introduced transformers, and transformers are an entirely new architecture in neural network design. So we have densely connected networks, and we have recurrent neural networks, and we have convolutional neural networks. Transformers are an entirely new paradigm, an entirely new type of network architecture.
RNNs and CNNs had been the flavor of the day to build language models. They had some interesting properties. They could support variable length sequences, CNNs could easily be parallelized, they had linear or logarithmic interaction lengths between tokens. The main issue was that they only modeled local dependencies between tokens. In CNNs, long-term dependencies required many layers and was lossy. Even GANs now are using self-attention due to their ability to model long-range, multi-scale complex dependencies, allowing us to capture more symmetries and patterns in the data within the input size limitation. Myth 6 in the 7 myths of ML research in early 2019 tried to dispel this idea that transformers were more parameter efficient, discussing lightweight and dynamic convolutions as an alternative with similar results on machine translation tasks. Transformers have their own architectural challenges. They can only work within a bounded length input size, and they have nonlinear interaction distance between tokens. And they're memory intensive as hell.
See, people used to process sequences of text using recurrent neural networks, but that had a problem. Namely, if you have a long sentence such as, Dave shared a beer with his friend, then to understand what his friend means, you need to know that Dave was at the beginning of the sentence. A recurrent neural network needs to store the fact that Dave was there until it processes that end of the sentence. And that can be very difficult to learn. So a transformer can do this in one step. It can go from anywhere to anywhere by using an attention mechanism.
Fast forward to November 2018. A chap called Jacob Devlin released a paper called Burt, Pretraining of Deep Bidirectional Transformers for Language Understanding. This was a game changer, not only because there's been a tsunami of NLP papers recently which modify or modulate certain aspects of this, but even more so, many of the titles of the paper pun on the word Burt, and I think that's testament, if nothing else, to the impact that this paper has had. But it was a bidirectional encoder-decoder transformer with 12 encoder-decoder layers, and it had a pre-training task, which was doing a master language model and next sentence prediction, and then it was also fine-tuned on downstream tasks. The larger version of the model had about 340 million parameters, which was quite large at the time. Now, because of the bidirectional context, it did particularly well on certain tasks downstream, so it was state of the art on question answering. Since Burt, there's been a tsunami of papers modulating some of the key findings that were in Burt. These papers even mention Burt or pun on the name Burt in the title. So we have things like Roberta and Albert and Distill Burt and Burt on stilts. But the problem is, for the average consumer like ourselves, what we really want to do is to understand the relative contribution of all of these different papers and being able to categorize what their changes are.
Authors will frequently combine different factors that could be leading to the advanced performance, such as introducing a new self-supervised pre-training objective, but also increasing the dataset size, having a more in-domain data composition, or increasing the size of the model itself. That's why this paper is so important, because it's taking apart all these different factors that can lead to performance gains and isolating them in this large-scale study of transfer learning in the pre-training, then fine-tuning pipeline for natural language processing.
So today we're talking about exploring the limits of transfer learning with a unified text-to-text transformer by Raffel and his colleagues from Google. This paper is basically a huge ablation study. It's just saying what happens if we change all of these different variables and how do those things affect the performance of these language model across a suite of tasks. Now, one of the cool innovations in this paper is that they created a text-to-text architecture. And what that means is they didn't need to change anything, even though they were testing against many different types of upstream tasks. Now, you might think that this is a form of multitask learning, and it kind of is, but it isn't. They still fine-tune it on all of the upstream tasks, but they did do a version where they trained it uniformly across all of the tasks. And after some tweaking, I was surprised to see that the performance wasn't actually that bad. What I mean by having a text-to-text is in the input text, you actually define what the task is. So you could say, I want you to translate this thing from English to German, and then you can say, hello, my name is Tim. And the language model will pick up what task do you want to do, and it will give you the result as well. And incredibly, there's no leakage between the tasks. It doesn't seem to degrade the performance in any way by having this text-to-text architecture. Remember to like, comment, and subscribe, and we will see you next week. Okay, so here we are. Welcome back to Machine Learning Street Talk. Today, we are going to be talking about a really, really cool paper that came out of Google, and it is exploring the limits of transfer. In fact, I'm just going to share my screen, so let's start again. Okay, so welcome back to the Machine Learning Street Talk YouTube channel. I'm here with my friends Yannick and Connor, and we're going to talk about a really interesting paper today that came out of Google. I'm just going to share my screen just to give you guys a bit of a flavor. So it's called Exploring the Limits of Transfer Learning with a Unified Text-to-Text Transformer, and it has 4 primary authors, but it's Colin Raffel et al. From Google. And I think that the main thing that Raffel wanted to demonstrate here was that since the Burt paper in particular, there's been an onslaught. There's just been a barrage of different papers with different variations, changing the pre-training objective, changing the amount of time we train, changing the size of the data set, and so on. And I think what these guys have really tried to do is to make sense of all of that, to kind of categorize the different types of tweaks that all these papers have introduced, and to do a huge ablation study to try and kind of understand where most of the benefit is coming from. Now, if we scroll down to the takeaways section, I think this is quite interesting. So the first thing is this paper introduces a new type of language model, so-called the T5 model, and it's a text-to-text model. So I'll just read this bit out here. Our text-to-text framework provides a simple way to train a single model on a wide variety of text tasks using the same loss function and decoding procedure. We showed how this approach can be successfully applied to generative tasks like abstract summarization, classification tasks like natural language inference, and even regression tasks like STSB. In spite of its simplicity, we found that the text-to-text framework obtained comparable performance to task-specific architectures and ultimately produced state-of-the-art results when combined with scale. So what this means is there are lots of different tasks in language processing, like translation and question answering, and normally you have a different input architecture. But now they've homogenized that. They have a unified architecture, so you can have one model that does many different types of downstream tasks.
Yeah, and one thing that I think is so interesting about it is with respect to transfer learning. Like when you're a developer trying to take this model for your application, I think it makes it so much easier to figure out how to fit your input-output into this kind of a model for the sake of this pre-training than fine-tuning pipeline. So I'm curious about what you think about the text-to-text input-output for some specific application compared to, say, Burt or these other ways where you would have to be more careful about how not only how you're defining your input-output, but also the generality of this pre-trained representation is decreased by having to be more specific with how you do input-output. So for that reason, I think the transfer learning, that's what I think is the key benefit of the text-to-text framework, is that it makes transfer learning easier.
Yeah, so I think this is very much, and they say that as well, depending on how you do the pre-training, even in this text-to-text framework, right? Now, maybe we should shortly, maybe people haven't read the paper, so in this framework, if you, let's say, want to do a translation from English to French, you would not train a model for that specifically, but you would simply say, translate to French, or translate from English to French, and then you put the text. So all of this is text. So the instruction itself is also text. And then they define various pre-training tasks where basically the model is supposed to fill in parts of this text. And I think the performance now really depends on how you do this pre-training, and I think that's one part that they show in the paper. But what I love about it is the fact that everything is text now. And it is so cool.
Yeah, I could also see it in the multimodal, the image Burt, trying to combine the images. And I guess sort of having this representation of text is super interesting to me because it makes it so you don't have to be so specific about how you define even the pre-training. I think because even just going from Burt has this mass language modeling objective that fits nicely into the sentiment classification because you do that next sentence prediction throughout the pre-training. But now I think you don't have to be as careful with the pre-training and then how that fits into the downstream task.
Yeah, though it's always what they we've gone through the takeaways, and the takeaways go we can do this and this and this, and then we combine it with scale. And then it becomes state of the art again. So it is unclear to me how much that scale influences this and how much the actual objective influences this, right? There's a lot of uncertainty with respect to all of these transformer family. For example, this next sentence prediction task, I think in the Burt paper, that was specifically mentioned as, we try to understand and so on. But then in subsequent papers, some people have claimed this isn't necessary. We just do masked language modeling. Don't worry about this pre-training, this next. So to me, it is still somewhat unclear where the magic is in these things. I don't know how you see that.
Yeah, it seems like, I definitely think like the Electra objective with the generator is an interesting way of doing this. It seems challenging to me. I hadn't read Span Burt before reading this paper, and I thought just that little modification that they do seem to show provides more benefits. So it's definitely like, I don't know, is there like a lot of opportunity for exploration in the self-supervised objectives? I don't think, it seems pretty explored to me. Like, it definitely isn't obvious some way of doing further. They've even tried the shuffling in ExcelNet of scrambling the sentence. It seems like they've pretty much tried it all to me with the pre-training objective. But yeah, it definitely was interesting to see all these little things combined together and like apples to apples compared in this framework. And I don't think anything else has done that at this level.
One thing that interests me, because I must admit, every time I look at transformers, there's always a small part of me that worries that I don't completely grasp what's going on. And for example, the Vaswani's original paper on transformers was an encoder-decoder, and then Burt apparently is an encoder, and the GPT variants and the NVIDIA, what was the large NVIDIA one?
Megatron.
Megatron, that's right.
Yeah, that's a good name for it.
And Microsoft, of course, have just brought out Project Turing, which is about an $18 billion parameter model. And those ones are, causal autoregressive language models. So those are only decoders. So can you guys put a bit of detail on the difference between them?
So yeah, in an encoder-decoder framework, you do what people originally did with LSTMs, right? Where you have an input and you encode it fully into like a hidden representation, and then you decode from that hidden representation. Now, you can have things like attention and so on going there, but basically you have two separate modules. One is the encoder and one is the decoder. And with for example, Burt is, as you said, just the encoder. So you put in a sequence and you get out an exactly same length sequence. So with pure Burt, you can't do something like produce language, technically. People do it, but technically it's kind of shaky how to do that. But what you can do is, for example, classify each location, do span prediction, and so on. But if you modify this Burt architecture such that your encoder, you just make it wider, such that you can put the input and part of the output as the input, and then you do this kind of masked attention such that the one token in the output can only ever look at its predecessors, right? Then all of a sudden you now have a classification where you can do language or sequence to sequence tasks using this. So I think the big thing here is replacing this two module thing with the funky masked attention, causally masked attention, such that you can do this decoding.
Well, aside from the translation models, like, when do you think it's interesting to encode only the inputs and then decode like only from the encoder's representation? Like, I guess maybe like summarization, you could take the original document and then encode it and then only decode from what the encoders produced. But like, so like, I guess the way I've been thinking about decoder only is that it doesn't make any sense to be encoding, like having explicit encoders and decoders with most of these tasks, like summarization, I guess.
Yeah, one has to say even the original transformer in attention is all you need was autoregressive in the sense that it had attention on the thing that the decoder produced, It was just that there were two separate modules for that, and now there isn't. It's all basically one set of parameters. So I think the main benefit might come from just the fact that there's parameter sharing between all of these things. Generally seems to help to just make your matrices larger but share them across the modules.
Yeah, what do you think about parameter sharing? It sounds like such an odd thing to me. That is it like, so I have like parameter, do they both get gradient updates? And then is it like kind of like how when you have like a quantized code book that you take all of the updates that came from every parameter that shares that weight? Or is it just like copying it? I mean, parameter sharing definitely seems like a way to save, especially the memory with respect to storing the model parameters. But it seems like odd, share the encoder and decoder parameters. I don't quite get like the idea behind that.
It's strange, isn't it? Because it's kind of similar to the way Siamese networks work. But, rather than happening in parallel, it's happening in series. So why would doing the same thing many, many times be beneficial? And why could you not shortcut? I mean, I suppose a neural network is like a computer program, isn't it? The idea is you are successively making transformations that transform data from one manifold to another manifold to another manifold. But why would you need to do that the same way in many intermediate steps?
Right, yeah, I agree. It doesn't make sense. It's like the same exact transformation applied again. But I guess it's gotta it's gotta have something to do with if you just, it's such a complex series of transformations that if you copy it and then paste it 8 layers later, it'll be making a significant difference, I guess. But yeah, that parameter sharing idea definitely seems like just like an efficiency thing, I guess. I don't know if I've read anything that is doing like a big study on parameter sharing other than like neural architecture search.
Well, what I meant with the original when I said parameter sharing was more like why should I have 10 weights in my encoder and 10 weights in my decoder when I can have 20 weights in a module that does both at the same time, right? It seems that seems to benefit more. Mm-hmm. Though with respect to parameter sharing, I would say the way you can make sense of it is if you think of these layers computing maybe subroutines of a program, and then like common subroutines, like aggregating features in a certain way, sorting them or something like this. And if you think of it like this, like a subroutine in a program, you can call it all over and it's kind of the same thing. But that is speculation. Yeah.
I like this concept that this over parameterization in the models as well, because several of the architectures that have come out recently, in particular, I'm looking at Burt. And that has a kind of teacher and student concept. It's all about knowledge distillation. And the idea is that you train a normal size Burt model, but then you come up with a student model, which is 40% smaller and 60% faster in inference. And you just get the student to clone the teacher. So, you just train them against each other. And then the student model retains about 97% of the performance. But it's a little bit like the lottery ticket hypothesis when, we ask the question, why do we need to have all of this over parameterization in the training phase?
Yeah, so I think the idea of this has been in production in many places. I think this is common in industry that you train big models and then you kind of just push them down because you want to serve them out, right? So the idea of that is not super new, but it's pretty cool to see this applies to transformers because, of course, they are very, very large and demanding. And it is still let's say, a mystery why any of this works, right? Because what is surprising is we get this small model that has such a high performance, but if we just train the small model from start with the training data, we can never get that performance. We need to train the big model with the same training data, but we need to train the big model and then distill it to the small model in order to get the small model to be so good. So there's like a weird interaction there with where you have to argue these large models, something about the over-parameterization makes the optimization procedure happy to accept the training data into the model, right? But then once you have it in the model, it seems like you can some sort of transfer the features that it learned by distilling it like this. It is still, I think this is still one of the weirder aspects of all of this, the fact that this distillation works.
I think you just a plug for your video on the lottery ticket hypothesis, Yannick. You said it perfectly. You said that in a way it's quite depressing that this is the way it works. It's a bit like you have a block of clay and you're kind of chipping away at it with SGD. And you said because in most of these network architectures they're so over parameterized, they actually contain n choose p subnetworks. There's this combinatorial explosion of different subnetworks, and at least just probabilistically, at least one of those subnetworks is likely to provide a good inductive prior for the problem. But this is a horrible way to go about it.
How does that pruning scale to transformers? Does that involve taking out the heads, or is it like how does pruning scale to transformers? How do you find a lottery ticket in a transformer?
Well, one comment we can make is James Raffel in this paper, he tried over-parameterization as one of the tweaks that we'll come to later. So he increased the model size. And his comment was that he just did it in the feed-forward section. He didn't touch the attention.
That's really interesting. Yeah, because the transformer thing is not obvious how you would prune that, right? Because it's like an operation on a set, and it's like, you can't just kill out the attention in an obvious way like you could with a a feed forward layer. But yeah, I think distillation is more of a testimony to the power of label smoothing and label regularization. Even if you have the naive label smoothing way of just having say 90% probability on the correct class and then uniform probability everywhere else, I don't think distillation is really transferring the features from the teacher model. It's just a more clever way of doing this, label regularization, I guess. Meta pseudo labels is a recent paper that also shows that just a more clever way of dynamically adjusting the labels in some kind of way seems to be a really good way to train these neural networks.
Yeah, that makes sense. Though, is it known how distillation works, let's say, across architectures? Because what I can imagine is that by doing this, by outputting not the labels, but the probabilities of the labels, you implicitly transfer the features because your student has the same architecture, right? It's a transformer and you're a transformer. So by outputting the exact probabilities you're getting on each class, that will sort of implicitly transfer the features because the same architecture should learn the same features given the same outputs, right? Is it known how I don't know that. Is it known how distillation works across architectures? Like if I distill this maybe to an LSTM or something?
Oh, I know there's a paper that does that takes the transformer labels and puts it in an LSTM. But yeah, I mean, the feature transformation, I think it's more so transferring its sense of embedding distances. So it's almost like a metric learning thing. It's showing you hey, this thing is it's kind of like a dog also, but it's very far from a ship, whereas this other cat is closer to a ship. I guess it's more of a transfer of the distances between the images in the data set than it is the features, I guess. But yeah, it's definitely super complex thing to try to
that is a smart way. Could there maybe be a distillation procedure where you use this notion of it's a distance metric and do some sort of contrastive learning where you say these two things should be closer together than this other thing? It seems like something like this, some combination like this should be possible.
Yeah, it sounds it kind of reminds me of how they use, kind of how neural style transfer uses the intermediate features, or I don't know, definitely a tricky thing, but it definitely seems interesting, that idea of distillation with distance, I guess, and thinking of it like that.
Okay, well, let's carry on reading a little bit of the paper then. So The second part, we started to talk a little bit about the encoder-decoder architecture, and I didn't completely understand that, but let's read this section. So there's a real contribution around architectures, and it says, while some work on transfer learning for natural language processing has considered architectural variants of the transformer, we found the original encoder-decoder form worked best in our text-to-text framework. Although an encoder-decoder model uses twice as many parameters as an encoder only, for example, Burt, or a decoder-only language model, so for example GPT, it has a similar computational cost. We also showed that sharing the parameters in the encoder and the decoder did not result in a substantial performance drop, while of course halving the total parameter count. So just to confirm, the original Vaswani model was an encoder-decoder model, or is it referring to, as Yannick was saying earlier, the original recurrent neural network seek-to-seek type models?
I think the original model was an encoder-decoder. I just kind of made the connection. So because the original sec-to-sec frameworks also always talked of encoders and decoders. Yeah.
I think it's because it makes intuitive sense, because the RNNs were learning a kind of sequential representation, and quite clearly there was an encoder phase where it was going from a sequence into this flat internal representation, and then a decoder phase. But transformers are a little bit different, aren't they? They don't flatten it into a representation in the same way. The data still seems to remain in the original time domain.
Yeah, it's though you kind of get to wash out the differences once you introduce attention into LSTMs and things like this. I think it's mainly about how you would program the things here than actual ideological or mathematical differences. But yeah.
Well, what do you think about like the position embeddings? Like that was when I first read the Attention is All You Need paper. It was such a bizarre looking way of doing the positional embeddings, and I think now they're doing these relative embeddings with like the Transformer XL. So yeah. I guess that's how they give them time, but it's very weird way. I think
you just know that they tried it without and it just failed hard, and then they were like, crap. Because the transformer by itself, it has no notion of positions in the sequence, right? It doesn't know where the information is coming from. It just knows, right? It can just query a kind of information. It can just address content like by its content. It cannot ask where it's from. And I guess they just realized, maybe the information that something is, at the beginning, at the end, or, too away from this other thing is, it just seems weird to put it even in, but that's how you know you need it, right? Because the original paper wouldn't have put it in if you hadn't needed it. But I find the way of doing the positional encoding using these sine waves and quite smart, right? Because what you're doing is you kind of overlaying sine waves, and then one is very slow, and then the next one is like faster, and by indexing a point in there, you can kind of measure distance to each of the scales. So the large sine wave gives you a large scale distance, it's sort of an encoding of your position where the model doesn't need to do arithmetics. The model can just think, what is my close neighborhood? And it goes to the fastest sine wave. And then it can think, what things are around me in a large sense? And it goes to the slow sine wave domain.
So I guess the way I think about it is it's giving the model a ruler. Because as Connor was saying, the Transformers XL, that introduced recurrence into the model, and then of course you need to have a relative position encoding for all of the chunks. But just coming back to Transformers for a sec, in contrast to a recurrent neural network where you're learning the sequential representation, so it has some concept of time built in, but I suppose it's actually more similar to the way reinforcement learning algorithms work. It's kind of everything about the past is compressed into now. But Transformers have this wonderful capability to model, essentially you can attend from any token to any other token, so you can learn these long-term representations, but does it then use those positional encodings as a kind of ruler to measure how far away those things are?
Yeah, I would guess that it is in like that 95% of why these things help is much more simple in explanation. It's just like, oh, this thing is at the start, right? It's just like a hard attention to the start of the sentence. If the start of the sentence says what or who, then that is an extreme bias to understanding what the sentence means, right? So I think a lot of the what these positional encodings give you is very simple, but then yes, I think some of it has to do with which words are my neighbors, which words are far away, which words are after me or before me, because that is very important, right?
Yeah, because one thing that springs to my mind is I'm really interested in the concept of symmetries. And of course, a CNN could capture a translational symmetry, but could a transformer capture the same symmetry? Because I don't like the notion that this positional embedding might hard code the pattern such that this particular pattern of text had to start at the beginning of the sentence or at the beginning of the input. Wouldn't it be good if it could learn the pattern in some sort of sense that it was, let's say, translationally invariant or even invariant to different scales? So it might be a pattern that happens at different scales of language.
Well, in some sense, it already can, if it just pays attention to the correct magnitude of the sine wave, right? If you think of learning a phrase like "My Little Pony," and you take the exact, so on one point on the side, it is like here on the sine wave, and then here, and in the other part of the sentence again, it is, because the sine wave repeats. I don't have good words for it, but maybe you realize that you have the same pattern of the sine wave in both locations, and thereby you can learn if after the word my, 2 words after follows pony, then I assign this meaning. And on the higher level, if you go up the sine wave magnitudes, you can learn something like, if there is a relative clause after a person name, then I assign the following meaning, right? So you can learn these big patterns on larger scales up in the layers. I think that this encoding of the overlapping waves is very cool exactly for that.
It's beautiful, and just to riff on that for a minute, intellectually, I don't know whether they did an ablation study where they took away the positional encodings, but if you think about it, the model has no concept of the relationships between the tokens, so it can only be using the positional encodings, and it raises all sorts of interesting things in my mind, because does that mean that it's only looking at the relative distance between the tokens? It's not actually looking at the context of the immediate words surrounding the tokens that it's attending to?
Well, who knows? I guess if you introduce these relative encodings, you have a very direct access, to the immediate, what is your immediate context, but even in the like old thing. So first of all, I want to say the ablation, I almost guarantee you, it does not work without the positional encodings, because like that's why they're there, right? From the beginning.
I think they actually in T5 they use like a learnable scalar encoding, so they get away from. I think they get away from the sign encoding.
Okay, that's cool. Like, yeah.
But
okay.
Yes, I guess the sign though, I just don't get it, because it's like it seems to like say it would say like word 8 is more similar than word 15. You know what I mean? Like it's sort of like arbitrarily putting words, closer.
In a way, right? In a way, yes. How I see it is, so in my bachelor's there used to be a group that did face 3D modeling, and they had a machine where they would 3D scan your face, and how it worked was quite cool in that it projected patterns onto your skin. First there was just black here and white here, and then there was black, white, black, white. And then there was black, white, black, white, black, white, black, white. So at the end, every little pixel of your face had its unique encoding of black and white across these different scales, right? It's like a binary pattern through time, and each pixel was unique in that. But it's not like neighboring pixels would always share the biggest part of their. So I think of it like this: you could capture the two cheeks, right? Because they are equal in their bit encodings, except for the very first one is black here and white here. But other than that, there's a symmetry in the higher layers. I think that you're right. Of course, it doesn't. In a way, it will say these two words are more similar than these two words. But if you do this across the layers, where the lower layer could say my neighbors are important, and then the larger layers could say my very far aways are important, that might do the trick.
Cool. Okay. Well, let's read a little bit more of the take-homes and the message. So the next one is talking about unsupervised objectives. Now, of course, in these self-supervised language models, the general modus operandi is that there's this pre-training task which might do next sentence prediction or a masked language model or even something else. And then, of course, you do the fine-tuning later. So it says, overall, we found that most denoising objectives, which train the model to reconstruct randomly constructed text, performed similarly in the text-to-text setup. As a result, we suggest using objectives that produce short target sequences so that unsupervised pre-training is more computationally efficient.
Yeah, I thought that was really cool too, to not reconstruct the entire instead of just reconstructing the mask tokens as a part of the whole original thing, you only do what's been masked out. And I think that that definitely probably speeds up the training enormously by having those just saying for inviting last, I bet that doubles the speed of doing this.
Yeah, so and they're saying it's because the output space is smaller. It just makes it more efficient to train. I find it fascinating, by the way, that would even work. So you give it an input of thank you, me to your party week, and the target is for inviting last, and somehow it manages to do that. I mean, that blows my mind.
Yeah, me too, especially because there's so many different ways to fill that out. Yeah, I can't believe that one works.
Yeah, but it's fascinating just to look at the evolution here of the different pre-training objectives on the self-supervised task, and of course in the Burt style model, it was doing something like this. So you had a random number of tokens, and then the target was the original text. So of course that's quite a large output space, and then there's deshuffling the words was I don't think that got particularly good results, and then there's this concept of masking the tokens. Is this the same as Burt? What's the difference between that and Burt?
I think the key difference is the span.
So I think in Burt they had two objectives. They also swapped some of the input tokens randomly, so that's why there's the apple in there. So but to your party apple week, and the Burt model was asked to also correct for that, basically. Whereas here in the just mask tokens, it's not.
I think this one is the mass. There's a paper called Mass, and that was the objective in that paper.
Yeah, do you think switching out last for apple is useful? I guess it looks like no. Or I guess not.
Well, as they say, right, most of these tasks that the people come up with tend to do equally well, but it seems like it is important that you do something like this, right? Because if you just just take a Burt model and just train it on question answering or sentiment class, maybe sentiment works. Everything works on sentiment, but if on question answering, it just doesn't work. So even though they say most of these things perform similarly, it still seems to be important that you do them and that you do this kind of thing, right? But I was also pretty impressed by the tasks they came up with, and I think that's cool.
Yeah, I think it even looks like a pretty big gain to go from 83 to 84.4 on all these glue tasks also. So I don't know if it necessarily the conclusion of they're all similar is right. Well, I mean, pretty similar, but it still seems like a decent boost in the.
Yeah.
But yeah, I also been thinking about like the Electra pre-training objective where they have the generator in a different way, and wondering like if they had put that into the pipeline, like what do you predict that would be as good, or would it, probably be also this performs the same as the others?
Well, here you have to refresh me on the Electra objective.
Yeah, that was the adversarial version. Go ahead, Connor.
Oh yeah, it's just like so you have your generator that is the one that's going to corrupt the text. So it's like a discriminator objective rather than predicting the mass token. So you have like a low parameter generator model that's filling out the mass tokens, but then the larger scale model is just seeing like what this like lower parameter generator thought it should fill in the tokens with. So it's like a discriminator objective rather than like reproducing the sequence. So it's giving you like 1-0 predictions of real or fake. So it's kind of like the GAN framework a bit.
I don't know what to think of that. It sounds like, so I know that GANs or something like GANs for text are still pretty far away. Something like this, it might work. It just seems like a GAN objective is a much lower information task than the actual language producing thing, right? But you have to weigh that against the fact that, for any given gap in a sentence, you could fill in like 20 different words and they would all perfectly make sense, right? And here you are with your training corpus telling your transformer, no, this one is the one that I want, right? And that's where something like a discriminator that just assigns a high probability to all those 20 words can come in and can really benefit you. So I have no guesses on ultimately whether that's going to be good or bad, and I mostly do not believe any numbers in any papers, because ultimately what happens is they come up with their new idea and they just throw more resources at it, or a bigger corpus, or it's a different trick here, or it is just so hard to compare these things, even if they go through the extreme like pains of doing all these ablations. It just seems weird.
What do you think about like the difference between when they have competitions to evaluate the papers? So it's like, do you think maybe that does a better job of like decoupling these sort of easy things to add onto it? Because if you have like a Kaggle competition, it's like everyone is going to be augmenting the data like crazy, ensembling the models and giving it as much compute as they got. Do you think maybe competitions are a better way to tease apart algorithms? Like, but I guess like the benchmarks don't seem to do that.
Yeah. This is one of the key things that Cholet is talking about in his measuring intelligence paper. He says that we've centered around this notion that benchmarking and competitions is the best way to get the best result. And Kaggle sometimes can produce perverse results because we become so fixated on the benchmark that the winning solution doesn't even generalize to the real world version of the problem.
Yeah, definitely. I mean, let's say there are two arguments here, or two modes. One is benchmark or competition is the way we evaluate things, right? And the other one is someone, reads all the papers, implements them carefully, does the same hyperparameters and the same amount of CPU cycles for all the models, and then reports the numbers. And both are just respectively, right? If you go for I'm on the side of the competition, because if you say just whatever the highest number you get, whatever you have to do for it, do it, right? And you're maybe cannot interpret where exactly your gains come from, but at least you get like an absolute number. This is how far you can push this, right? With everything you've got. Whereas if someone goes and just implements all the things, we've seen this, there's this kind of famous paper that said all GANs are created equal, right? And they implemented all these GANs, and then the authors of the Wasserstein GAN, they came along and said, clearly we stated in our paper that our algorithm only works with, I don't even remember, RMS prop or not with Adam or something like this. And this paper, they had our hyperparameter grid is these algorithms, right? And they said in their paper, it doesn't work like that, right? And then so it seems to me that all options are bad, but if push comes to shove, I am more on the side of the competitions. But I think ultimately you as a practitioner, the best thing you can do is look at all of these different papers and just kind of try to crystallize out, not really believe anyone individually, but crystallize out. If you see tricks over and over again, if you see architecture types over and over again, that's probably what's going to work.
It does make me think of some of the comments that Cholet was talking about, though, in his paper. I mean, he used the example that in the 1980s, people like Marvin Minsky had quite narrow definitions of AI, and it seemed to center around how well you can perform a task. But it's a different metric for humans and algorithms, because if an algorithm can beat the world chess player, that doesn't seem particularly impressive, but if a human can, that's very impressive, and that's because the human is learning how to become that highly skilled. And I think increasingly when we look at, it reminds me of when we talked about the Uber Trailblazer, because that was all about a system that learns and produces its own curriculum. And I think that these competitions and these benchmarks, they're so narrow-minded that they stop us from making progress in what artificial intelligence should be, which is being able to learn things dynamically.
Well, is the question even to make progress in artificial intelligence? Because it, like, you know, for I don't know, a company like Google, it's just if their translation model is better than everyone else's, then they get money, right? So that's. But the other thing is, with regards to intelligence, I think if you give a human the same amount of time in actual raw, let's say, compute time, when you like neuron firings versus GPU cycles, and if you give it the same amount of memory where it can write down all the things, I would not be surprised it becomes much better at chess. I think the impression of the humans, like, they're so good because also there's limited time, and we kind of get a feeling of how just hard it is to do that. But yeah, I have a feeling we'll be doing a measure of intelligence talk very soon.
I think we will. I think we will.
Like, what do you think about like the Dawn bench, like the idea of like limiting the computational resources for a task and for a competition? Because it seems to me like you can't really have this thing where you have like fair computation for everyone and then still do something interesting with the models, or like interesting on the scale as if it was unbounded. So I definitely think like it seems to me like the best effort for like machine translation and all that wouldn't even be to play with the algorithm, like the bitter lesson, to just figure out how we can train 100 billion parameter transformers or a trillion parameter. And it's like whatever is the difference between like the TPU and the GPU and how that enables these like larger scale matrix multiply. It seems like the chip engineering is a more promising direction for this kind of thing.
Yeah, and the data collection. I had some interesting conversations with a friend once, and I was basically arguing the point that, you know, you should get equal resources and things like this. And his point was very clear that, and I found it very good, that there are effects that only come out at scale, right? Mm-hmm. There are effects that these models capture that they can only capture because they have 1 billion parameters and because they have 50 terabytes of training data. And it is true, the only objective real number that you have is if you have unbounded computation, if you have unbounded everything, how well can you perform? Now, it's an entirely different task to say you get this many CPU cycles, because if I want to engineer something on a mobile phone, I care about that, right? But it's a narrower field, let's say.
That's That's quite a nice segue to talk about the datasets section of the paper, because some of the papers in this area, like Roberta, for example, they discovered that Burt just simply wasn't trained for long enough. It was undertrained. And as I think we'll find out in this T5 paper, training more is one of the most effectual strategies. But just to read this datasets section in the take-homes, we introduced the Colossal Clean Crawled Corpus, C4. They released this, by the way, which comprises heuristically clean text from the Common Crawl web dump. When comparing C4 to datasets that use additional filtering, we found that training in-domain, unlabeled data could boost performance in a few downstream tasks. However, constraining to a single domain typically results in a smaller dataset. We separately showed that the performance can degrade when an unlabeled dataset is small enough that is repeated many times over the course of pre-training. And this motivates the use of a large and diverse dataset like C4 for generic language understanding tasks. So they started off with this C4, which is this huge data set. It's 745 gigabytes, and I suppose what surprised me is that's filtered. It was 6.1 terabytes, and after they filtered it, it got down to 745 gigabytes. And by filtering it, they removed all of the JavaScript. I think they only took sentences that ended in a period. They did it. I think they did some deduplication, but it's surprising how much they could filter away.
Yeah, I actually thought another thing that was kind of interesting is like, even though the current pipeline is like there's tons of unlabeled text available, and then it's like it almost seems like natural language processing is the thing to benefit from this unsupervised pre-training than fine-tuning. But it seems to me like, so they're able to get 750 gigabytes of text from the entire internet, and then they have like 20 gigabytes of Wikipedia plus the books. But then another interesting thing in the paper that you're going through, if you go to table 12 in the paper.
Yep, on my way.
Yeah, it's like look, the supervised multitask pre-training is it's only like 3 points behind on Glue. So it's like, what will scale? Like probably the supervised, like people are coming out with supervised natural language processing data sets like every day. So it's like, I would actually predict that the supervised multitask pre-training is going to be the more scalable thing in the future, because you can't get that much unsupervised. I mean, you get a lot now, but as people just build out and label these data sets, it might be that the paradigm shifts and images is the thing that we think of this unsupervised pre-training pipeline as, because you can go drive a self-driving car around and get like more images than you could even store in a data set. But it seems like maybe the supervised task is what will scale with language.
Oh, that's interesting, because I think the take home from this paper was that it is still better to do unsupervised pre-training, but it does seem to indicate that the magic of unsupervised training is simply that you get more data. So you're training for longer with more data, and that allows you to learn better. But they did some interesting experiments, didn't they, with this? So they tried not even doing the unsupervised pre-training at all. And then they did something similar to Microsoft's MTDNN, which is when you do multitask learning. So you do a uniform task learning over all of the tasks, and then you separately fine-tune for all of the downstream tasks. And that seems to significantly improve the performance.
Yeah, I definitely think that multi-stage, like do your unsupervised mass language modeling, and then even if you just do the same self-supervised task, but like on in-domain data, I think that's another huge characteristic of this, is like this gain you get when you're doing the ablation of the data sets. And if you're doing your pre-training on the Wikipedia data, you'll do better on like Squad, and you'll do worse on like Cola, because it's never seen an unacceptable sentence before in Wikipedia, so it has no sense of that.
Yep.
But yes,
yeah, maybe that's. I mean, the large part of the effect is just gonna come from the fact that you have never seen text like you're gonna get in these tasks, right? Whereas with the images, it is gonna be the same images or it is going to be natural images all the way through. It's not like the visual question answering task all of a sudden has like a big arrow on the image, like this thing, what is this thing called? right? And and you've never seen that during training, right? So I think that is really the distinction here. The fact that they now frame everything in text, and there's structures, and there's unacceptable sentences and so on, that the model has never ever seen during training. It can't make sense out of it. So these on-task pre-training might be exactly doing this, like providing the model with a sense of the type of data that it's going to get during the actual fine-tuning stage. And that, I mean, they kind of shoot themselves in the foot a bit here by saying that, because it puts into question how much you can gain by all this huge pre-training, right? If ultimately our explanation is going to be, well, you still need to see the kind of data that your task is on, and if you do, then you're not that much worse.
Yeah, how interested are you in like meta learning, where the definition of it is like domain adaptation, or like rapid changing to a new like kind of environment? Like I like things like kind of like MAML, where they try to find like a good set of initial parameters such that when you do domain shift, it like quickly adapts to this, you know, going from like Wikipedia to, I don't know, one of the like the books corpus or something. Like, what do you think about meta learning and domain do you think like it's possible to really have like an unsupervised representation that can work for every domain, or do you think you necessarily need to have this other mechanism that does domain adaptation?
I think one way of describing it is there are more similarities between language corpora than there are dissimilarities. So I suppose by doing that unsupervised training, you are capturing as much useful generalizable information as possible. But as you say, there are many words which mean different things in different domains. So in the financial world, the word default is a very, very bad word. With regards to meta learning, I always find these meta learning papers, it's a bit, because we just don't have that many tasks, even in NLP, and even though people are coming out with new data sets all the time, it just seems there's this limited amount of tasks and the kind of limited ways in which things are diverse. And then to truly claim you now have an initialization that works on general language seems a bit of an overclaim of all of these papers. I've seen the same thing with this. There was this visual task adaptation benchmark by Google, where the same thing, right? You want to pre-train on something like ImageNet, but then you only have 1,000 samples for all of these other tasks. It just seems these tasks are all too similar, such that you can't really then make the statement that you found something general. So I'm a bit skeptical in that way, but I think it's a very cool field, and if possible, then I think that, especially for practitioners, that will be game changing if like you can do something like this. I have to say, with respect to the data set, it's called Colossal, and I think the community might be running out of words that describe large things. There's Megatron, and then there's XLNet, right? And the Transformer X, and the so I wonder how high they can push this word game. And also they released this, which means that someone at OpenAI must have been having a heart attack, because how can you release something that's so dangerous? That's like this is like 10 times as dangerous as the OpenAI corpus would have been. Exactly. I mean, one comment I did want to make is it's actually not that big. So their data set, which they call Real News-like, I think that's, or Web Text-like, I think that's their equivalent of what they did with GPT-2. So they filtered this corpus onto high-quality news articles, and I think that meant things that were linked from Reddit that had been upvoted at least 3 times. And this is only about 35 gigabytes, but the glue score is significantly higher than the filtered C4.
Yeah, I had to say, how the heck is it that it's only 20 times larger, all the internet text, compared to like news articles particularly?
Yeah.
Well, maybe the internet isn't that interesting.
I think it's like also like kind of, this is kind of like where like the privacy thing gets funny? It's like if you were to like go through like everybody's Facebook messages or like their Twitter direct messages and conversations, like I feel like you could get so much more like good text data if you were to like break that kind of like privacy thing and get your chatbot data.
Well, how enticing. Well, I think especially, so it is especially, these things are especially worrying because it seems like these transformers are getting so large that in essence, they're just kind of remembering the training data and interpolating between the training data. Because, so I always get the impression that to really make the next step in something like NLP, you need a grounding of this knowledge. I always think of this Cholet's example with the ARC challenge, where you have a picture and these pixels are black, and then there are like 3 blue pixels and 2 orange pixels going away, and it's clearly like something is bouncing off a wall. But we can understand it because we live in the physical world where things bounce off things, right? I think the next step needs to happen in terms of grounding, and these models don't have it. And so all they can really do, and all they do, is they interpolate patterns that they see in the training data. And these models are getting so large that I'm pretty sure they just remember the entire training corpus, and they kind of figure out how to mix and match, right? So they were like, oh, here's a noun, and then the sentence kind of starts with these words, so I'm going to finish it with this example from the training data, right? Or with these mix of these two. I'm pretty sure they don't learn very sophisticated things. They just learn how to mix and match training data.
There was the
privacy comes in through that. So even worse, right? There's this XKCD comic where they start writing the email with the next meeting of the rebellion leaders will be at, and then the autocomplete,
Well, sorry, my question on the idea of like language grounding is like, what do you ground it in? So you could have like these text-based adventure games where you get this text prompt that's like, you're in a dungeon, you see this thing on the table, what do you want to do? And you navigate the world with text in that way. Chatbots are kind of like grounded in that similar way, where you have a reaction from what you're saying. And then there's things like point scale navigation, or the Allen Institute's RoboThor thing, where you're like navigating a visual world based on like language cues. There's also something called read to fight monsters, which is where you get the like description of the game you're about to play in language, and then you go and play the game. So it's like, in order to ground the language, you have to have the context around it, I guess. And I guess it's unclear how you would define that.
Well, these text adventure games and all of these things it's a nice idea, but if you want to make this machine learning capable, you need a lot of it, right? So you need a lot of text adventures, and you're only going to get that by someone writing a procedural generator of the text, and that means you're not dealing with language, you're dealing with a procedurally generated grammar where you basically just always kind of look for the same patterns of words that the simulator writer put in. It's what I mean by grounding is more like if I say there is a car around the corner, I live in the physical world. I know cars are objects, they're on roads. A corner means a house corner in this particular case, right? So there's like a road, and there's a road here, and there's a house in between, and I can't see the car, but it's around the corner.
So I love Cholet's concept, though, that intelligence is very much linked to the world and the environment that we live in, and that's his major argument why there can be no explosion of intelligence. But I really like some of the stuff you were saying before as well about neural networks are basically just memorizing machines, and you could argue that we are the same. I mean, philosophically speaking, if we could remember everything, and this conversation now is just us regurgitating things that we've picked up from random places, and we're not really thinking fluidly and intelligently. Of course, that's not true. I mean, what Cholet would say is that we have this problem in deep learning that there's minimal generalization. So in order to learn anything, we have to do memorization. And there was this wonderful paper a few years ago that said that deep learning algorithms don't extrapolate, they just interpolate. And the argument that it gave was, let's try and learn the scalar identity function, which is basically f of x equals x. So it's the simplest function in the whole world to learn.
That's just mean.
I know, but this
That's
is
being
really
mean
tragic.
to a neural network.
I think they trained it between -5 and 5, and then they tested it in inference outside of the training range with a whole bunch of different activation functions. And you know what? None of them could extrapolate. Isn't that tragic?
Yeah, but how important? Yeah, I guess. But it's such a hard concept to define. Like back to this idea of like language grounding and this idea of go look at the car that's around the corner. Is Google just released this like street view images data set where you're going through the street view and you're navigating based on language. Like with enough data, you can interpolate between vision and language probably. You probably can navigate very well with language. So then, so I guess it's like extrapolating, is it necessary and can we even define it? Because then you're like, okay, it can do vision and language, but it's still not intelligence. Like what else do you want to add to it? Like audio,
Yeah, true, right? It's at some point, because embodied cognition, which is basically what I'm talking about, right? That you live in the world. We only live in the world via our senses, right? So there is our senses, and then our brain that has been optimized to make but it's just input signals, right? That we interact with the world, and one can argue that if you give a neural network enough of these different modalities, it might be able to make the same connections. That is true. Yes, absolutely.
And in a super way, because like Tim said, you can recall everything you've ever experienced, like instantly.
Yes. Yeah.
Yeah, that would be a curse. That wouldn't be a good thing. But I suppose we can. Sorry, go on.
The notion of this generalization, I also don't know how. So if you think of this identity function, like who's to say that we don't want the network to learn a function that goes like this and then back to the mean, right? It's only because you tell the human, or the human kind of does this extrapolation, but based on what? That's my question. Like, do we have the intrinsic notion that the pattern must go on with the identity function, and how are we doing this? I think that's the big question to answer.
Yeah, it's interesting because, as you say, in the real world, we have some kind of useful inductive prior which allows us to reason about how things in the world relate to each other. But in mathematics, if it's just such a simple function, why would it be so difficult to extrapolate that?
Well, I guess like also one thing is like sort of like why I got really interested in generative adversarial networks is I think like studying the way like a generator that produces like high dimensional output rather than classification labels is such a more interesting way to look at generalization, because you can give it like this data set of cats and you get to be like, did you design a new cat according to like my sense of, I just think it's another more interesting like thinking about generalization is models that are like creating things that are, and not just labeling them.
That's quite interesting though, because is that generalization or not?
Yeah, it needs to like disentangled representations is another thing I really want to get into is like when it can learn how to like take the hat off the guy, just put sunglasses on him, like take apart the factors. That's super interesting. But yeah, so
okay.
Do you want to continue going down the paper, or?
Yeah, sure. We keep digressing, but it's no bad thing. I think that's what this whole channel is about. It's called Machine Learning Street Talk for a reason. Now they talk about training strategies, and I think here what they're talking about is, what struck me is if it truly was a multitask model, that would be wonderful because they got best results by fine-tuning in the end on the respective tasks. But imagine if you did just have this language model which was multitask. This is almost like something you get in Star Trek. You say to the model, I want you to translate something from English to German, and it's hello something or other. And the model will, without any leakage between the tasks, just give you the result. They got pretty good results on that. I mean, that just blows my mind. Though
again, there you have to say that it isn't really, the model is probably not really learning the meaning of the sentence I want you to translate this. Probably they just prepend that exact sentence to all the translation tasks, right, and then fine tune it. And the model just needs to learn that particular combination of tokens is now indicating the language, right? It's not understanding the I want you to do something.
No, absolutely. But I suppose what it is doing is if this huge model is a computer program, it's kind of partitioning the model. It's delegating responsibility. So
yes,
some part of the model is responsible now for doing translation. But what's interesting is the interconnected and shared nature. It's not like it's saying, oh well, the top part of the model is going to do the translation. It's actually reusing representations. I mean, it's interesting to talk about the MTDNN paper from Microsoft, because that does multitask learning as part of the pre-training before we fine tune. And the take-home message seemed to be that by training on multiple tasks at the same time, it gives you a kind of regularization, because you're learning representations that are useful and have utility across all of the tasks.
Yes, that's very, very believable. I think it would be extremely interesting if we had better introspection into these text models to see what's really going on, like how far up are these things shared? Or is it just the case that maybe just the word embeddings are shared, and then the model just divides itself, and we just like, okay, you two attention heads, whenever there's translation, you do that, right? And all you others do the other thing, right? And then maybe as tasks are similar, it would be very interesting to perform like introspective analyses on exactly these models, how much the representations are shared, where the subroutines are reused across, and maybe you find some super interesting things. So there was this paper a while ago that did zero-shot translation. I don't know if you've seen something like this, where what you do first is you pre-train on, let's say, English, and then you just fine-tune the word embeddings of French, and then you can like input English and output French. I don't exactly remember how it went, but you can do like zero-shot translation without ever having trained on that particular language pair.
Is that because some of the recent neural translation models, essentially what they do is they translate, if it's trained in a multilingual way, they'll translate all of these different languages into a common intermediate representation. So in that sense, it could translate between almost anything.
It wasn't the same thing, but I'm gonna find it here. Okay. Because it was pretty interesting, and it basically showed that there is something going on, like an abstractive language understanding. I'm not saying grounding or intelligence, but just like an abstractive notion of language, where maybe, okay, English and French are close together, but there's something going on that's beyond just a single task. And it would be super interesting to see how these multiple tasks and objectives are handled in the representations throughout the layers of the transformer.
I wonder whether someone's done a paper on that, because when you started to put your hypothesis on the table about it being partitioned rather neatly with the attention heads, that was quite convincing to me. So maybe it does do that, because if it is just, if it were a horrible, fully connected neural network, then of course it would be very, very difficult to understand what's going on. But for some reason, having clean partitioning across the attention heads, that seems like it would be more likely to happen.
Yeah.
It kind of is like a conditional computation model too, with how it routes it to the attention heads a little bit. Or, nah, not really. Yeah, but like multitask learning, and I actually hadn't understood that. I thought it actually was understanding that, like summarized. I thought it like understood that and then summarized it. So I thought that it did have a sense of that. Like I thought that one of the cool things about the text-to-text task is that maybe if you had this new task, like like who is the pronoun referring to, you could like prefix it with that and then the sentence, and it would learn it a little faster than if you had, say, embedded like 0000100 indicates like pronoun disambiguation or something like that.
Yeah.
Yeah, I mean, it goes to show as well that I love this concept that neural networks are basically computer programs, albeit ones that are differentiable. Because, as you say, there is actually no difference just to using a piece of text. It's still just processing it in exactly the same way with almost no leakage.
But do you think it picks up the new task faster? So this is like, to me, what's so interesting about text-to-text being something that can enable transfer learning. Do you think it picks up the new task? Like, let's say you come up with some, I don't know, like some prefix task in natural language, and then you give it the task after the colon. Do you think it will maybe learn that faster than as if it was like totally zero shot, and then like there's some, say, embedding vector or extra like normalization parameters that tell it that this is this new task?
Well, I suppose it would be hard to give it a one hot vector because actually the tokens are encoded using some word vectors, so it's in a much higher dimensional space. But assuming that you replicated something similar, I don't see why it would make any difference.
You could just put some garbage there, but just always the same garbage, right? But something that does not in natural language mean the task that you mean it to mean. You get like, so instead of saying translate from English to French, you just say, I don't know, sandwiches are nice. But you always whenever there's translate from English to French, you always say sandwiches are nice, right? And then that would be maybe a cool experiment to see whether it actually helps. That it has probably seen the phrase translate in that context somewhere in the training data, and it, there might be a bias towards there now being multiple languages. I don't know, but
right,
it could be. It's a cool experiment. It's a cool idea.
Yeah, like maybe the training curve is a little bit faster because it is still taking that summarize and then hitting the embeddings table with it and getting a sense of what it means. Hopefully, like the embedding has a sense of summarize.
Yeah.
But yeah, that's less exciting to me. I thought it was smarter than that.
Yeah, unfortunately, it's never as exciting as it sounds at first sight. I mean, just to kind of talk about the last thing that they really played with in the paper, and it's almost depressing that it's the scale and the amount of training that made the largest difference to the results. So the baseline on glue, and by the way, there's another thing called super glue in it, and we can pull up the paper for that, but that's a more sophisticated version of glue-like challenges because we were getting too good at the glue benchmark. But yeah, the baseline was 83.28. And when they did 4 times as many training steps, it went up to about 85.33. So that's about 2 points up. And the biggest improvement was when they increased the size of their network, the number of parameters by 2. And they did that not by changing anything in the intention heads, but by increasing the number of parameters in the feed-forward layers. And they also did 2 times as many training steps. And that gave them essentially 3 points of improvement, which is huge.
Yeah, I think what will happen is that like this, we were talking earlier about you only get 750 gigabytes of like taking all of the text from the internet, and then with the more clean data sets you get like 20 or 30. So I think what will happen is that you'll train this really large model, and then it'll just do like one pass through it, or like it won't I think size is going to scale better than training steps, because it seems to me like they'll figure out how to train like a 100 trillion transformer before they'll figure out how to get like the corresponding data set size, because like the two have to go together with that scaling, I guess.
It's quite interesting as well, because there are some weird things that happen when you increase the training size. When they did the multitask learning, for example, if you just do a uniform prior over the tasks, some of them did quite badly, and of course it's just a balancing thing, because you're kind of under training on some tasks and over training on other tasks, and they came up with a temperature parameter to kind of to weight the relevant tasks as a function of how much contribution they had. But it's not just the difference between the tasks. It's also the concept of the unsupervised training objective dominating the downstream tasks. So there's quite a balance. I think the most important thing is the kind of transfer rate between all of the different training objectives.
Yeah, it's cool to see, like, not cool, but you see that same phenomenon of like class imbalance, like where you have way more like dogs and cats than frogs. And then also in this task framework, it's also like, yeah, it's definitely interesting, like the class imbalance problem, and then seeing it on the task level also. But yeah, I mean, you would think that like the text prefix would be able to like do the, like, I guess that's kind of why the conditional computation thing is so interesting. If you could have this special like sparse routing that comes from the task embedding, that might be the best way to overcome like class imbalance, task imbalance, or maybe like it's kind of also like catastrophic forgetting and continual learning in a way, I think, like a little bit. And that, I think the latest solution to that from the Jeff Clune paper is like neuromodulation and sort of another kind of sparse routing, I think, or something like that. I'm not exactly sure what happens in that paper. But yeah, it's definitely interesting to think of the composition of the multitask data sets and the size of them.
Absolutely. I mean, that's pretty much the paper, to be honest. But I think it was really, really good just to explore, if I change this and if I change this, what makes the biggest difference. And clearly, when you look at the history of all of the kind of the papers, let's say in question answering over the last few years, it was the Burt paper that really gave us the significant boost. And since then, we've probably got another 10 points worth of improvement, but it's balancing out. But when you look at a kind of 2-year time horizon, it was this transfer learning, and maybe all transfer learning means is training for longer on more data. But that was what gave us the biggest improvement.
Cool.
Okay, I mean, just another comment that might be worth making is just how this is democratizing. It's so easy now just to download a pre-trained model, just this unified T5 model that we're talking about. I mean, you can download it, they've published it online, or you can train it again yourself, and you can just do really sophisticated translation. Just I guess the point I'm trying to make is that a few years ago, if you wanted to do really good speech recognition or translation, you couldn't do it yourself. You had to use the Microsoft or Google Cloud platform, it's called Cognitive Services on Azure, because these are things that it was just accepted that you couldn't do it yourself because you didn't have enough data, you didn't have a good enough model, you had to pay for it. Now it's really becoming quite democratized. Yeah,
I think it's also like, like you can just form your own data set and then be like, answer these questions about it. And I also think it's so important to remember that like the MTDNN like multi-stage thing too, where like if you can get like, say you want to get all of the deep learning papers and make a data set of that, like before you start labeling it, you can also do the self-supervised learning on that data too and have that pipeline, which I also think is interesting.
I mean, and that maybe like another way to think about it is, why is language different? Because a high quality language data set apparently is 35 gigabytes. That's nothing. Whereas facial recognition, that seems different. The Google FaceNet paper, they've trained it on about 26 million faces, and that's why it works so well. And that has incredible value. I mean, I wouldn't be able to download that from Google. I mean, if I did, it would be very, very valuable. So it's almost as if language is now becoming more democratized than vision.
Yeah, it's just a more compressed representation, right? I think we've just not figured out yet for images how to compress them in a way so that we can reconstruct them. But ultimately, all you care about is what ends up in your brain, right? So for language, we found this good notion that we can encapsulate the sound waves in just words. But I think for images we just have not yet done this, and maybe in the future, once we figure that out, the data sets might just become smaller in size. The question is how much informative content is there.
Maybe one way of looking at it though is that because language and vision are both, they're unstructured data, it's in the unstructured domain, But if you think about it, vision is much more unstructured than language.
Yes,
language is
definitely.
actually very structured, isn't it? You
Yes.
have atomic tokens, and you can model very, very clear sort of relationships between where they appear, and it's one-dimensional. So maybe that's the reason why you actually need much less, pre-training data for language as you do for vision.
Yeah, possibly. Yeah, I mean, there's you only have to kind of learn the grammar of a language, right, to make sentences at least. But in order to learn what a natural image is, you have to like learn correlations between all the pixels, and no one tells you what's good and what's not, right? I'm not sure. Maybe it's also because vision is just like almost like a 2D image of the actual 3D world with objects. So it's sort of a projection, of something. I'm not sure. I have another question. What do you think? How far will this we encode everything as a text, this task go? Because I'm pretty sure if I were to produce something like a chatbot or something like an assistant, like an Alexa, I would just hard code all the single commands, and that would work much better for now.
Well,
right?
that's actually a really interesting point, because if there was that famous chatbot from Microsoft called Tay or Tao, and you should be incredibly careful releasing anything into the world which learns and which isn't explicitly programmed. And
I'm not even talking about learning, right? It's just like, do you train it with this notion of I'm going to really understand what the human wants in like a deep learning kind of way, or if I were to do this, I would try to understand what it means and then just regex match to my predefined lists of tasks that it can do.
Well, I think defining the regex list would be so challenging. Like if we're like on Lyft customer service and you and I are both frustrated about like the map has made an error, I think we're both going to describe our problem so differently in natural language that that's the problem. And then I guess it's like this idea of like fast adaptation. It needs to quickly adapt to how Connor describes his frustration with the map.
Yeah.
And then quickly adapt to how Yannick is going to describe his frustration with the customer service. So yeah, I think like that domain adaptation and like getting quickly to the new domain is going to be the key thing that makes this applicable.
But I think there's something interesting here, though, which is that, first of all, people think that chatbots are all about AI, and they're really not. They are just a user interface, and they are best constructed with static rules. The only natural language processing that you get is things like intent recognition. So what do I want to do? Because if you think about it, if you did have some kind of an unstructured output, I mean, imagine you plugged a GPT model into your chatbot, and you could say to the chatbot, how are you feeling today? And the GPT model will say, yeah, I'm feeling great, thanks. But what value does that have? It's completely useless. And it's also unquantifiable. If I wanted to test this thing, if I'm releasing this thing in my production system and I wanted to write tests and I wanted to understand what it was doing, it's completely useless. I've got no idea.
But what if it was like it was pre-trained on like the chatbot? It's like a chatbot, and then you can fine-tune it somehow on like all the deep learning papers, and then you can ask it questions about that. It would be sort of interesting.
That would be sort of interesting.
I just find this notion of formulating the task as text, and then what this paper doesn't do is then how then can you do something like the meta learning that Connor said is quick at it? Can you throw, if you do this enough, can you throw a task at it that it's never seen in that form, given the textual instructions, right? And then I'm thinking back, I've seen a presentation by Richard Socker a while ago of Salesforce, where he pretty much proposed the same thing, but he said all of NLP should basically be question answering. So you always have a question and a context. And he had this notion of you can output text to answer the question. So you can frame something like next sentence prediction, or you can do something like sentiment analysis by simply outputting text, right? But he also had this notion of pointer networks. And these, I find, have just gone down. I don't know if they don't work or if they're just not hip. But he always uses these, or his group always uses these pointer networks, where he says, you can either output text or you can point to something in the context or in the question, saying like, here's the here's the answer. I think, because they already formulated this kind of all of NLP should be in this one task structure, very similar like here. Maybe we're ready for a recurrent, like for a resurrection of the pointer network here. Just interesting parallels.
It kind of reminds me of like multi-hop question answering, like that kind of idea where it's like you need to say like, you need to answer a question such that you want to go and ask 2 more questions to like better answer the question. Yeah. That context-free question answering is one of the key things that they claim this T5 model does well, is that you can be like, when was World War II, or any question, and it just knows it because it's memorized it.
Yeah, of course, but the GPT-2 was also its thing, right? But there they didn't fine-tune, they just pre-trained the language model, and then they posed the question, and magically the answer came out, and just, right, because it was in the training data somewhere.
Yeah. I love this parallel between, in the olden days, we used to have knowledge graphs that were explicitly computed, and we would say in that knowledge graph that Barack Obama is 45 years old. And the thing is, it was so onerous to build up the knowledge in the knowledge graphs, and the information was often conflicting. So they used to write unit tests, which would check for logical equivalence. And actually, that's happening in language models as well. So, my friend Marco Ribeiro, he has this concept of coming up with, semantically equivalent adversarial examples or logical tests. So what he might do is he might ask the question, how many boots are there in this image? And the answer would be 3. And then the logical consistency question would be, are there any boots in this image? And you expect it to be yes. And you can use all of these things possibly to generate adversarial examples, which you can then use to pre-train or to fine-tune the model. Or you could potentially use it as a way to say, no, I don't like this model, I'm not going to put it into production. But I'm quite interested in this engineering reality, because we have these unstructured models, and coming up with some non-interactive way to reason about its behavior is really interesting.
But even humans are terrible at this. Like, humans would fail these unit tests so hard, because if you've ever, so there is this thing in like personality science called the Big Five personality test, right? And it's kind of statistically derived and so on. And it's a self-report test, and if you fill that out, they would always ask you the same thing in 2 different ways. They'll be like, I often feel sad, and then it will be like, I don't often feel not sad, or they do it smarter, but still. And then like the amount of times where this number isn't the negative of this number is just astounding. It's like, hey, human, you said you always feel sad, but here you said you're mostly happy. What's going on? Right.
You know what's even worse? When I applied for my current job, they gave me these silly psychometric profiles, and they said I was only an X out of X on this dimension. And I said, why is that? And he said, you took 10 milliseconds too long to answer the question.
Crazy, but
anyway,
maybe these, I mean, I see where these kind of tests are going, but it's at some point it becomes more a question of the tester, right? Of how well these things are really logically equivalent, right? Because language is just so subtle, and the boundaries to things like sarcasm, the boundaries to things like hyperbole are so narrow sometimes that it is super hard to write this procedurally. Again, if we could write these things procedurally, we could solve the problem.
Yeah, but again, this is something where we have the potential, because the reason why WordNet, for example, I mean, that was also a knowledge graph, and it was very brittle, and it didn't get updated very often, and it didn't know colloquialism, so it didn't know that this word means something different where we are. But possibly the composability and distributed nature of deep learning architectures would allow us to start with a kind of pre-trained base model, and then potentially have a high velocity model, which is kind of learning colloquialisms that are relevant to me.
Yeah, definitely.
Well, guys, I think we've come to the end of the show, but it's been emotional.
Yeah, this was fun.
That was good.
Brilliant.
I just want to address maybe viewers that we're trying different things. So last week we had an author on. It was more like interview style. The week before we had like many different people. We're in a field where none of us was really, well versed. We just kind of, someone had something to say at some point. So if we don't know ourselves what is the best and the most interesting. So we're looking very much for feedback on what people like and what is interesting and what isn't, and should we be super prepared and very technical for people that know everything, or are most people like, well, you talk about things that I don't even understand, you should introduce the concepts first. So this is kind of an appeal to the listeners or viewers to leave us comments, poke us with complaints.
And remember to hit that subscribe button and the notification bell, because if you don't, we will be seriously unimpressed.
Cool. All right.
Peace out.
Cool.